Section 5.3, the fundamental theorem of calculus. Pretty much every branch of mathematics, I think, has its fundamental theorem for that particular branch of mathematics. For algebra, it has to do with zeros of a function, like roots of a function, x-intercepts on the graph of a function, that kind of thing. For trig, I think it has to do with arc length on the unit circle. We talk a lot about unit circle in trig. And for calculus, the fundamental theorem of calculus, and there's actually two parts to this thing, but it makes the connection between that process of differentiation, right? We'll call that differential calculus, and the process for integration, right? Or integral calculus. Or we could say that it makes the connection between our tangent problem, remember it was our basic problem that we discussed with differentiation, and the area problem, right? The area under the curve, which is what led us to the integral, right? That whole limit of some things, okay? But there are two parts to the fundamental theorem of calculus that we're going to talk about. The first part is, I don't want to say it's not useful. It makes that connection between the derivative and the integral, the fact that they are ultimately inverse processes, right? So actually remember, because when we do an integral, we're finding an antiderivative ultimately. But the second part is actually the more useful part, because that's the one that's going to actually allow us to, or gives us a process to evaluate integrals, right? So we'll talk about the first part. I'll show you what that's all about, but our primary focus is going to be on the second part, because that's the part that is more useful ultimately in being able to evaluate an integral. But just a little historical context for this. And if you find yourself, if you like history, or if you have an interest in history, and you have the opportunity to take a history of math class, you may want to check into that. I mean, if some of that stuff is kind of interesting when you actually see, not just the math itself, but where it actually came from. When it was developed, how it was developed, who developed it, why, and so forth. So some of that could be interesting if you like history. So history of mathematics. But anyway. So we're looking back in the 1600s. Now you may recognize the name Isaac Newton. That's probably the name that most of us recognize. You hear about Newton, a lot of different things. But it was one of his teachers, Isaac Barrow, back in Cambridge in England in the 1600s, that actually kind of realized that the process of differentiation and integration were inverse processes. And so you kind of got to think about the problems that we were talking about, like the tangent problem, right? The slope of the tan line, the rate of change of a function, that kind of thing. And then the integration or the antiderivative part, which is the area under the curve, right? But somebody had to actually make the connection that, hey, wait, recognize that these are actually inverse processes. Okay, so they were kind of two separate concepts that eventually they made the connection between the two. Newton and Leibniz were actually developed and refined calculus into kind of the mathematical method or process that we know today. They were working on this about the same time. And again, this is back in the 1600s, but they were working independently of each other, supposedly. Right? So Newton was working on his stuff, Leibniz was working on his stuff. Now again, Newton is the name that we're more familiar with. Leibniz, that derivative notation that we use, that dy dx notation or that ddx notation, that's actually called Leibniz notation. Right, so he's given credit for that notation, but there's a lot of the concepts that Leibniz developed that are incorporated into calculus. But they were developing this at about the same time, and I think Leibniz was the one that actually published something first, and then Newton published something, and of course, then it became a matter of who actually gets credit for developing this process, or that we're calling calculus, or this whole kind of branch of mathematics. So there was an argument between them, and everybody took sides, and do we give Newton more credit? Do we give Leibniz more credit? So they decided to send it to the penultimate mathematical society of the time, which was the Royal Mathematical Society of England, to make the determination as far as who would get credit for the development of this branch of mathematics. But it turns out that the president or the head of that Royal Mathematical Society of Mathematics in England was Sir Isaac Newton. So guess who gets credit for developing calculus, right? And when we say develop calculus, it's always like we say, they actually discover something new. It was more taking all the concepts that they were familiar with, these processes that were developed, and and kind of organizing it into a formal process, right? So instead of just piecemealing things, let's actually come up with a formal process, define all the notations and the processes and the terminology, et cetera, et cetera. Right? So ultimately, then Newton is given credit for that. We call him the father of calculus. Leibniz, though, does get pretty good credit on this. I mean, even though his name is not on the top of the list, you put his name second on the list, and he gets a lot of credit for a lot of this stuff. But anyway, so there's a lot of that kind of stuff that goes on in the history of mathematics. When you look at some of the things that were done in history and development of some of these different concepts. So that's why I said if you like history and you kind of get into that kind of stuff, looking back on some of the history and how some of this was developed, you may find that a little bit interesting. All right, but back to the calculus. So here's what we're going to do. We're going to let our function, or let a function g of x, be defined as the integral from a to x of f of t dt. Now for this first part of the fundamental theorem of calculus, you've got to be real careful with variables, and we always talk about terminology and notation. When we talk about differentiating a function, what are you differentiating with respect to, or what are you integrating with respect to, right? That kind of thing. Watch the variables, because sometimes we do get a little loose with our variables and we're not particularly clear. We know what we mean, but again, you always have to write exactly what's needed in terms of the notation so that there's no misunderstanding of what's being said. All right, so we're defining this function g of x as the integral from a to x of f of t dt, where f is continuous. There's good old continuity again, as always. Continuous on our closed interval from a to b, where x is some value between a and b. So ultimately what we're doing is we're making our upper bound of our integral a variable, right? So we're allowing that to change. The bottom, or the lower limit, is fixed, right? It's a constant. Now, if x is also fixed, if we pick a value for x and say, okay, let's take the integral from a to b, and I pick a number for b, then the integral is a definite number, and we call it a definite integral, right? And we can actually calculate the value of the integral. We also, from our previous discussion, know that when we talk about the integral, we're talking about the area under the curve, right? The area under that integrand from a to b. So if f is a positive function, then we know that our function g of x, now again, watch the terminology and the notation here. What is g of x? G of x is the integral, right? So we're giving the integral a name. We're calling it the function g of x. So g of x, being the integral, represents then the area under the graph of f from a to x in this case. All right. So again, you just got to be careful with the notation. We have different variables floating around here. Now, from our previous discussion, we know that g of x is the antiderivative of f. Right? So we talked about back in 5.2, where the area under the graph of our integrand is equivalent to the antiderivative of that integrand. Right, now here's where the variables are going to come into play. So you got to be careful. Notice that g is a function of x, a function of that upper limit, but our integrand f is a function of t, all right, a different variable. So here's what the fundamental theorem of calculus part 1 says. It says that if f is continuous on a closed interval from a to b, then the function g, denoted by g of x, is the integral from a to x of f of t dt, where x lies between a and b, somewhere in our integral, is also continuous on the integral from a to b, and it is also differentiable on the open interval from a to b. Remember, we always say continuity on the closed interval, differentiable on the open interval. And here's the tricky part. G prime of x, the derivative of g, is f of x. Now again, remember, g is the antiderivative of f, because if g represents the integral of f, then the antiderivative of f is g, right? But also notice that the antiderivative of g, or excuse me, the derivative of g here ends up being nothing more than our integrand evaluated at that upper limit, evaluated at x. Because again, g is a function of x, so g prime also has to be a function of x. Now I'm going to give you an example here in a minute that's going to kind of better kind of illustrate what this is talking about. So kind of take it for what it is at this point. If I define my function g as an integral from a to x, where I make the upper limit a variable, it's movable, then the derivative of g, the derivative of the integral, and you think about those as inverse processes, is simply the integrand evaluated at that upper limit. Okay. All right, so let me give you maybe an example in detail and show you how this works the way that it does. All right, so I'm looking at number 1, or part A as I have it here. Finding the derivative of the function. Now again, this is where you've got to be careful in what they're talking about in terms of the function that you are differentiating. What am I differentiating? I'm looking at the function g that is defined as the integral from 1 to x of ln of t dt. And so according to the fundamental theorem of calculus, we're saying that the derivative of g, right, the derivative of the integral, and those are just inverse processes. They undo each other. Remember composition of inverse processes? Gives us the integrand ln of t evaluated at that upper limit x. So g prime of x is natural log of x. Now I broke this down and just to show you again how this comes about in a little more detail. So remember, we're calling g our integral from 1 to x of ln of t dt, and then we're differentiating that. We're finding g prime. So in other words, I'm saying let's differentiate, let's find d dx of the integral from 1 to x of ln of t dt. Okay? So here's what I did. I said, let's just replace ln of t with f of t. When you think about it, let me back up a second. When you think about, okay, first, if I just want to work what's in the bracket, I want to find the integral of natural log of t dt. I don't even know what that is off the top of my head. We know the derivative of ln of t is 1 over t. But what's the antiderivative of natural log of t? I don't know. So even if you have a function, an integrand there that's not easy to find the antiderivative of, and actually that's something you look at in Calc 2, where there's actually a little process that we use to find the antiderivative of natural log of t, or natural log of x. But anyway, if I just look at the integral part of this thing, and I want to find the antiderivative of ln of t, it's not actually an easy thing to do. But I'm just going to play with the notation. Let's let f of t take the place of ln of t. Okay? So now I'm looking at the derivative with respect to x of the integral from 1 to x of f of t dt. All right, so I just replaced ln of t with f of t. Now, before I go to the next step, I'm going to mention the fundamental theorem of calculus part 2, because it actually comes into play in the next step. So I want you to understand why. So I'm going to mention this, and then we're going to come back to the FTC part 2 once we're done with our examples. Here's what the fundamental theorem of calculus part 2 says. It says that, again, if f is continuous on the interval from a to b, now notice we're dealing with the definite integral here, a fixed upper and lower limit, then the integral from a to b of f of x dx is the antiderivative of f, call it cap f, evaluated at that upper limit minus the antiderivative evaluated at the lower limit. All right. And again, I'm going to come back to that, and then once we finish with our examples, and we'll get into the details of exactly maybe why that makes sense. But the integral from a to b of little f of x dx is equal to its antiderivative, which is cap f, evaluated at the upper limit, minus the antiderivative evaluated at the lower limit. So then when we come back over here, and I've got that derivative with respect to x, so d dx, that integral of 1 to x of f of t dt, then the integral of little f, again, is cap f, right? So cap f of t, evaluated from 1 to x. The little notation I'm using there, we'll talk more about this little notation as we go through. But there's our antiderivative of little f, which is cap f of t, evaluated from 1 to x, right? Lower limit, upper limit. And then FTC part 2 that we just looked at said you can evaluate your antiderivative, cap f, at the upper limit, so that's cap f of x, minus your antiderivative evaluated at the lower limit, which in this case is 1, so minus f of 1. Now we still have the derivative of this thing on the outside. All I'm working on here is the integral. So then I'm looking at the derivative of f of x, cap f of x, minus, the derivative, minus the derivative of d dx of f of 1. All right, so remember, the derivative of a difference is equal to the difference of the derivatives. That's one of our basic properties of the derivative, or rules for differentiation. Well, what's the derivative of cap f? Well, remember, cap f was the antiderivative of little f, right? So what's the derivative of cap f? Well, that's got to be little f. So if cap f is the antiderivative of little f, then little f is the derivative of cap f with respect to x. So then the derivative of cap f of x with respect to x is little f of x, minus the derivative of f of 1. Now remember, the derivative of a constant is 0, right? And that's what f of 1 is. I mean, if you plug 1 into your function f, I don't know what f is at this point, but whatever it is, it's a function. I can plug 1 into it. I'm going to get a constant. And so the derivative of a constant is 0. So that's why, notice in our fundamental theorem of calculus part 1, it doesn't matter what that lower limit is. It could be any constant, it doesn't matter. But we're defining the upper limit as a function of our variable x in this case. So what does that leave me with? Well, that leaves me with just f of x, little f of x, which, again, remember, what is little f? Little f is your integrand. So ultimately then what this says, just kind of going from the first step to the last, is that the derivative of the integral from 1 to x of ln of t dt ends up being just f of x, which is ln of x. Right? So there's one example just to kind of show us that the derivative of the integral of a function is that function evaluated at that upper limit. Right? Again, that's where we're defining the variable. Now there's going to be a couple of little tweaks on this, right? So a couple of things we'll mention, but that's the basics of it. That's how it works. Okay? So again, it may seem a little weird when you see the statement ultimately, but that kind of hopefully explains how that process actually comes about. That's kind of what they use to develop the process. So that's part A. If you look at part B then, now notice cap f of x, I'm just using different letters and such here. So I'm defining cap f of x as the integral from x to 10 of tangent of theta d theta. All right. Now back to one of our rules or properties of the integral that we talked about in the previous section. Remember, we made note that if you reversed the limits of integration, then you would change the sign on the integral. Remember that whole integrating from left to right versus right to left kind of thing? So that fundamental theorem of calculus part 1, we're defining our integral with a variable upper limit. So we're going to get back to that notation, get back to that setup, in that if I have my variable in the lower limit, so I've got the integral from x to 10 of tan theta d theta, let's reverse our limits of integration so that we're going from 10 to x. Right? And then by doing that, like we said, we're going to reverse or change the sign of our integral. Right? So that's just one of our basic properties, and it gets us back into the form that we can work with for FTC part 1. So now I can take the derivative of cap f, and again, watch your notation. So cap f is the integral from x to 10, or now cap f is the opposite of the integral from 10 to x of tan theta d theta. So then cap f prime, as we just showed, is then that integrand, tangent of theta, evaluated at our upper limit, which is x. And then there's the negative that we had out in front of the integral. So again, defining our function as an integral with a variable upper limit, its derivative is the integrand evaluated at that upper limit. Now, since we are differentiating, then our basic rules for differentiation are still in play. Mainly, here I'm talking about the chain rule when we look at example C. Now, I'm going to talk about this two different ways, right? Kind of the formal way, and then a little more streamlined process. And ultimately, we're just going to make use of the streamlined process, but I want to show you how this works in the more formal manner first, so have a good understanding of this. Also, maybe he gives us a little bit of review with some of our notation that we've used. And so in this case, again, because we're working with multiple variables, right? And so again, we got to be careful when we're with respect to, well, which variable are you actually talking about? What are you differentiating with respect to? What is your function of variable of, etc., etc. So for part C, I've been finding our function h of x as the integral from 0 to x squared. Right? So notice our upper limit is still a variable, yes, but it's not just x, but it's a function of x. Right? Our integrand is the square root of 1 plus r cubed dr, and then dr. So here's what we're going to do to integrate this thing. Since we want to find the antiderivative with respect to that upper limit, here's a little process that we're going to talk a lot more about later. In session 5.5, we're going to talk about a whole substitution method for evaluating integrals. So this kind of gives us a little bit of idea how this is going to work. What we do is we replace x squared, replace that upper limit with a variable. We just use u. You see u used a lot by default. It's just tradition. Nothing special about u. Just like there's nothing special about x. It's just tradition. So now watch what we're doing. So I'm replacing x squared with u. That way that upper limit is just a single variable. So now I've got our function h of x as the integral from 0 to u. Our integrand hasn't changed. That's still square root of 1 plus r cubed times dr. So then what did we say before? We said our derivative of h. If h is the integral with a variable upper limit, then its derivative, h prime, would be the derivative of that integral with respect to that upper limit, right? But now our upper limit is u. So I'm differentiating with respect to u, the upper limit, that integral from 1 to u is square root of 1 plus r cubed dr. But then again, remember, h is a function of x, so its derivative is a function of x. Since we replaced the upper limit, a function of x, with u, we still then have to differentiate u with respect to x. That's our good old chain rule. Right? And again, that's why I harp so much and I preach so much about making sure you're not just doing processes here, but you have to actually understand how the process works, and especially in terms of the variables and the notation and the terminology that we use. You've got to understand the notation, because otherwise this probably makes no sense. Okay? But ultimately, what are we doing? We're differentiating the function h with respect to the variable x, right? So first, I'm differentiating that integral with respect to its upper limit. This part. Okay. And I'm differentiating with respect to u. But then we have to differentiate u with respect to x, because our function is a function of x. X is our independent variable. All right, so the first part then, the derivative of the integral with respect to u, well, we said we just plug in the upper limit. So our upper limit, which is u, so I just plug that into our integrand, and I've got square root of 1 plus u cubed, times the derivative of u with respect to x. Remember, what is u? U was x squared, back here. So I differentiate u with respect to x. I've got du dx equal to 2x. Right, so there's our chain rule. And then we back substituted in place of u. I plug back in the original x squared to get everything back in terms of x, because again, I'm defining h prime of x. So back substitution replaced u with x squared, and now I've got h prime of x equal to 2x times the square root of 1 plus x to the 6th, right, x squared cubed. That's the formal process. And when you look in the solutions manual, that's the process that they're going to follow. They're going to use this little substitution method and all of that. But notice, so here's kind of a little more streamlined process. Instead of going through all of that, let's just do exactly the same thing we did before. That if I'm going to define h of x as the integral from 0 to x squared in this case, square root of 1 plus r cubed dr, let's just do what we did before, and let's go ahead and plug that upper limit into our integrand. So that's what I did here. If we just, like I said, bypass all of this, and we just plug in the upper limit into our integrand, right? So it's 1 plus x squared cubed. But I do then have to differentiate that upper limit because it is a function of x, right? So if I have something other than x there, I also then have to multiply by its derivative, and that's basic chain rule because we are ultimately here differentiating a function. And so there's our 2x times the square root of 1 plus x to the 6th, right? So yeah, the first method in this case is more formal and it's a lot more particular in terms of the notations and so forth. The second little process, which was of course a lot quicker, it just kind of streamlines that process. So that's all I'm going to ask you to do with that. Because like I said, ultimately, fundamental thermocalculus part 1, it makes the connection between integration and differentiation, being inverse processes, etc. But FTC part 2 that we're fixing to talk about is the more useful part. That's the one that we're actually going to work with primarily because it's going to show us how we can actually evaluate an integral. Okay. Yeah, but FTC part 1 could be tricky. So you're playing with different variables and notations, and that obviously has its own issues. All right, so then back to FTC part 2 that I mentioned earlier. All right, so here's what FTC part 2 says. It says that if f is continuous on the interval from a to b, then the integral from a to b of f of x dx is the antiderivative, call it cap f, evaluated at that upper limit, b, minus the antiderivative evaluated at the lower limit, a. All right, so again, we're at cap f is any antiderivative of f, and we'll get into that as well, because remember we said when we find the antiderivative of a function, we always tacked on that plus c, all right, that arbitrary constant. But that is, again, that f prime, cap f prime, is little f. Right? So we showed that you could tack on a constant when you're doing the antiderivative, but then when you differentiate, since the derivative of a constant is 0, right, it didn't matter. Right, but that was our discussion that we had back in section 4 or 9. Maybe give a little more context, a little more understanding. Okay, well, why does that actually work? Well, we talked a lot about velocity and position. Right? So remember, our velocity function is the derivative of our position function. So if we have our position function s of t, its derivative s prime is v. So if v is the derivative of s, then that makes s the antiderivative of v, right? Where again, remember, v is the velocity, rate of change, and the position of our object. S gives me the position of the object. It gives me the displacement. If I evaluate S from point A to point B, right, S of B minus S of A gives me the displacement of the object from point A to point B, or time A to time B if you wish. So that's exactly what we were talking about before. If we take the antiderivative of our velocity function, so if I look at the integral from a to b of v of t dt, with t representing time as it typically does, then the antiderivative of v is s. And to evaluate this definite integral, it's that antiderivative s evaluated at the upper limit, which is b, minus the antiderivative evaluated at the lower limit, which is a. Right, and we had that whole discussion back in the previous section about how the integral of the velocity function, the antiderivative of the velocity, actually gives us the area under the velocity curve. Right? That was our whole discussion we had, or led up to, in kind of summarizing what was said in 5.1 actually. Right? But this gives us the process that we can use to find or evaluate an integral. We simply find the antiderivative of the integrand, evaluated at its upper limit, minus evaluated at its lower limit. Okay? There's always upper limit minus lower limit. Doesn't matter which one is larger or smaller, quote unquote. Right? So we'll see examples along those lines as well. Right? But it's always b minus s of b minus s of a, or the antiderivative at the upper limit b minus the antiderivative at the upper limit a. Okay? So FTC2 then gives us a much simpler method for evaluating the integral rather than having to go through that whole limit of something, right? But that's, again, where the whole integral came from, or the idea of the integral anyway. All right, so for example, now and I'm going to go, let me just mention something here first before I continue with this example. So I'm looking at example part A. Evaluating the integral from -2 to 5 of 6x dx. So we said we find the antiderivative of 6x, right? So using our basic power rule, that would be 6x squared over 2, or 3x squared. And so then according to FTC part 2, we said we take our antiderivative evaluated from -2 to 5 in this case. And notice the notation I'm using there. I expect you to use that notation. So we find our antiderivative, then you need to indicate what your limits of integration are. What are we going to evaluate that function to or from? All right. So that's notation that you would expect to see for every integral or every definite integral that you're going to evaluate. Now, just to mention real quick, we said that when you find an antiderivative of a function, so for an indefinite integral, ignore the limits of integration. Our most general antiderivative of 6x if we just had the integral of 6x dx, it's 3x squared plus c, right? That's our general antiderivative. But notice I didn't bother putting the plus c up here. You can put it if you wish, but I don't actually need it. And here's why. Because when you evaluate this thing, so what are you going to do? You're going to take the upper limit, 5, you're going to plug it into your antiderivative. So I plugged in 5, so 3 times 5 squared. Now I'm going to write this and I'm going to erase it because, like I said, you don't necessarily need this. So if we do a plus c right there, minus 3 times -2 squared. Now there would be a plus c here as well, but if you distribute the negatives, you actually end up then with a minus c. So notice what happens. Plus c, minus c. All right. So in other words, I'm taking 3x squared plus c. I guess I'm going to go ahead and do this down here just for the heck of it. Right? So if we included, and I always like to do that if I have multiple terms just to show that I'm evaluating that whole function. So we would do this, we would have the 3 times 5 squared, right, plus c, when I plug that in, minus, we've got the 3 times -2 squared plus c, right? And so again, we can evaluate this, we can evaluate this. Here's the plus c. I'm going to circle that. Here's the plus c, and here's our minus c. So these two guys are always going to cancel out. They're always going to subtract out every single time. Okay? Because, I mean, they're going to represent the same constant in both cases, right? Whatever the constant is that you care to put on there. So bottom line, when you are evaluating an indefinite integral like we have here, we always tack on that plus c. This would be -2 to 5. But with the definite integral, you don't have to put it because when you evaluate the integral, you end up subtracting out that c anyway. Okay? But you can put it, if you want. It doesn't matter. We just don't need it. All right, so then again, all you're doing now is just basic calculation. So you're plugging in your upper limit, 3 times 5 squared, 25 times 3, 75. And then 3 times -2 squared, -2 squared is 4 times 3, so 12. 75 minus 12 gives me 63. As usual, the least of my concern is the actual calculation, which, just watch your calculations as always. Don't make some careless error there. It's all about the antiderivative, right? So the main thing is you've got to find the antiderivative of your integrand, and then you're evaluating it at the upper limit minus the antiderivative evaluated at the lower limit. So part B, integral from 2 to 8 of 1 over x dx. Right? So here's our recognition. Remember that the antiderivative of 1 over x, we said, is the natural log of the absolute value of x. Now, the absolute value is not essential in this case because notice both our upper and lower limits are positive. But we said when you're finding an antiderivative of 1 over x, it is natural log of the absolute value of x, not just ln of x. Doesn't matter in this case because we're integrating over a positive interval, but if those limits happen to be negative, it would make a very big difference. So then we're evaluating from 2 to 8. So there's again that little notation that we use. We show that we're evaluating from lower to upper limit. So then we plug in our upper limit. So I've got ln of 8 minus evaluate at the lower limit. Okay. And then this is maybe just reminding you of one of our properties of exponents, properties of logs, excuse me, that we talked about way back in the first little review section, that you can take the difference of logs and write that as a log of a quotient. Right? Remember, the product of logs is a log of or the sum of logs is the log of a product, and the difference of logs is the log of a quotient. Okay. So that's all I did here. I just rewrote that. Now, if you don't remember that, I'm not gonna make that a big issue. But we try to simplify things whenever we can. So I've got natural log of 8 over 2, which I can simplify as natural log of 4, right? But if you left it as this, I'm fine with that. If you don't remember all those properties and rules, that's okay. Part C, example C, integral from 0 to 1. 3 plus x square root of x dx, right? So again, ultimately, or initially at least, it's all about finding your antiderivative, right? So whatever is necessary to do that, right? So I'm working with 3 plus x square roots of x, which would be x times x to the 1/2, which is x to the 3/2. So I just rewrote that as 3 plus x to the 3/2, so that we can use our power rule to find our antiderivative, right? So then our antiderivative of 3 is 3x. Antiderivative of x to the 3/2 would be x to the 5/2 divided by 5/2, or times 2/5. That's, again, just basic antiderivative with power rule. And then we're evaluating from 0 to 1. And notice, again, like I said, I like to put parentheses around my antiderivative, especially if there are multiple terms there, to show that I'm evaluating that entire function from 0 to 1. And so then we plug in our upper limit, which is 1, minus plug in our lower limit. But notice if we plug in 0, we always like 0. It makes our calculations easier. But if I plug in 0 into these guys, I'm going to get 0 here. I'm going to get 0 there. So I've got 0. And so then ultimately I end up with 17/5 if you do the calculation on that. As always, we like exact answers better than approximations. So if you are finding or evaluating an integral, we try to give exact values as much as possible. Now, that's a terminating decimal, so if you gave the decimal there, that would be fine. That'd be, 3.4. Okay. But don't approximate these unless you're asked to do so. Right? I want to see you find the antiderivative, so you have to show that. You want to show what you're plugging in, so you need to show. Now, you don't have to show me every little nitpicking calculation, all right? But you do at least need to show what you are plugging into your function. Show me that you're plugging in that upper limit minus plugging in the lower limit. Now, you can do all the calculations in one step. I'm fine with that. But you at least need to show where those calculations are coming from, all right? So in other words, don't just go from here to there. I'll dock you for that. I want to see what you're plugging in. Okay. All right, that's it for that section. And we'll continue to talk a lot more about that definite integral going forward.